Welcome to the afternoon session. This is a large-scale session as you look at the talks. And first up is Nick Hutchins from the University of Melbourne, and we'll be giving a talk on the existence of very large-scale motions or superstructures in wall-bound and turbulent flow.
Okay, so this talk, as Joe said, is just going to look at the very largest scale structures in turbulent boundary layers, the so-called superstructure. And to do this, I'm going to be looking at data from 3 separate facilities, but more importantly, data covering 3 orders of magnitude in Reynolds number. So from a Kalman number of around about 500 up to Kalman numbers of 600,000 in the desert. So just to give some kind of introduction, maybe the biggest clue that there's something really large going on in the log region of turbulent boundary layers is in the energy spectra of the streamwise velocity fluctuations. And I know Ivan went through this on Monday, but I'm just going to assume no one was listening or you've all forgot. I need to make this energy map clear, and I think it's pretty difficult to interpret, but if I just show you how we build it, it's really simple. So what I'm looking at is the energy spectra as a function of distance from the wall in a turbulent boundary layer. So the data here is from a boundary layer at a pretty decent Reynolds number of 7,300. The figure on the bottom shows the mean velocity and the RMS profiles, and then the figure on the top is showing the energy spectra at each position from the wall. So this is at the first position from the wall. For the top figure, the x-axis is distance from the wall, which we call Z because we're from Australia. The y-axis is the energetic length scale normalized by boundary layer thickness, and the z-axis is the magnitude of that energy. So as I move away from the wall, that energy spectra rises to a pronounced peak, which we call the inner peak, and it's fixed in viscous wall units. So it's, and it's due to that near-wall cycle of streaks and quasi-streamwise vortices. So it's fixed at z plus equals 15 from the wall, and it has an energetic length scale of 1,000 wall units. As I continue moving away from the wall, you see that small-scale regime gives way to something much larger that seems to peak somewhere near the midpoint of the log region. And now this peak is fixed in outer scaling. So it's got a peak energy at 6 delta, and the distance from the wall is about 0.05 Z on delta. And then as I continue away from the wall, that energy is just going to drop to nothing by the free stream. So what I can do is take this bread slice plot and put contours around it at given levels, and then just spin this around so we're looking down on that surface. And that's this energy map that I'm going to be talking about through this talk. So it's just showing me the magnitude of the energy at each distance from the wall and at each wavelength. So in this view, it's pretty clear that we've got this bimodal behavior. We've got that peak fixed in viscous units, and which we know is due to the near-wall cycle, or we believe it is. And we've got that other peak fixed in boundary layer thickness, which we weren't so sure what was causing that. So it was pretty natural for us to want to take a look at what these fluctuations in the streamwise velocity look like that could give rise to that 6 delta long energy that we're seeing in the energy spectra. At the time, we didn't have the capability to look at field of view that big with PIV, so we resorted back to hot wire anemometry, and we deployed span-wise rakes of 10 hot wire sensors into the log region of the boundary layers. They were spaced such that they covered just over 1 boundary layer thickness in the span-wise direction. And then it's a very simple experiment. We just sample those 10 wires simultaneously and then use Taylor's approximation to project that in space to build up some spatially approximate view of what these largest scales might look like. That's what I'm showing here in these top 2 figures. So we're looking at streamwise velocity fluctuation. Red is high speed, blue is low speed. And what we saw was kind of surprising. We were expecting to see these 6 delta long structures, but then occasionally we'd see these much larger features meandering through our measurement array, and maybe they're just chance concatenations, I'm not sure. So the middle figure shows just the low speed fluctuation, and you can see this large meandering region that's about 14 boundary layer thicknesses in length. And just to complete the view, the PIV on the bottom shows that what we were getting from our PIV at the time in Minnesota was a really truncated view of what these structures actually look like. Okay, so the next thing I want to consider is what this means in terms of Reynolds number. So from a simplistic point of view, at least in terms of the streamwise velocity fluctuations, the near wall cycle, or the near wall streaks, and these very large scale structures in the log region are pretty similar. They both consist of meandering regions of high and low speed fluid. They've both got similar aspect ratios, so they're both geometrically kind of similar, and I'm just going to use that for this very simplistic analysis. So when we look back at that energy map, we've got these two peaks, and more importantly, just look at the length scale. We've got an outer scale that's 6 delta, and we've got another peak at 1,000 wall units. And so if we think in terms of the ratio of those superstructure events to the near wall cycle, then it's easy to see that it goes as 6 RE tau and 1,000. So I'm ignoring all the scales between here. I'm just considering the peaks. So if I resort shamelessly to using cartoon representations of those two structures, which I'm doing here, we can look at what this means in terms of scale separation at some given Reynolds numbers. So the near wall cycle I'm showing as the solid contours, and they're 1,000 wall units long. The superstructure type events I'm going to be showing as these transparent contours, and they're 6 delta long. So you can see at very low Kalman numbers of around about 180, there's almost no separation between these two scales. 6 RE tau is 1,000 wall units, give or take. And as we increase Reynolds number, obviously we see increasing scale separation. RE tau of 500 is where I've got my first experimental data. And you can see that we've only got a ratio of these scales of about 3. If we refer back to the energy map, you can see that at these very low Reynolds numbers, there's no sign of that outer peak in the energy map. The red circle shows the location of that near wall peak, and the red plus sign shows where the outer peak would be if it existed, or where we think it would be. We continue increasing Reynolds number, Kalman numbers of 1,000. We've got a bit more scale separation, but I can't really see any signs of that outer peak there. It's not until we get to 2,000 or 3,000 that we begin to see the outer peak emerge in the energy map. So we really begin to see those superstructures emerge. And this continues as we increase Reynolds number. Not only is the scale separation increasing, but the magnitude of that peak is becoming stronger and stronger. And that's all the way up to 14,000, which is as far as we've gone in the laboratory, pretty much. So one point I want to highlight is that not only the scale separation is trivial. Obviously, that's what Reynolds number means, pretty much. But the point to note is that as Reynolds number increases, the magnitude of that peak increases, which means that the energy of the fluctuations due to these superstructure type events is growing and becoming increasingly comparable to the energy in the near wall cycle as Reynolds number increases. So if we look at one of these cartoons from the higher Reynolds number, we could ask what this means in terms of the near wall cycle. And certainly I think it was John Kim on Tuesday highlighted the point that this near wall cycle is self-sustaining or autonomous. And I think that that's the case, but just because it can regenerate without any outer influences doesn't necessarily mean that it isn't influenced by these large-scale events in the log region. It just isn't necessary for it to regenerate. So in reality, of course, the wall's going to be carpeted with these viscous scales, and they're going to exist all the way below this superstructure type event. But what we see in reality is that far from being a random distribution below the superstructure, we see these kind of preferential alignment with the phase of these large scales. And other people have noticed this before, Rodham and Toe and Itano, and it's basically what Ivan's talking about when he looks at amplitude modulation near the wall. So whether they're aligned or just preferentially strengthened, we're not really sure at this time. I'm going to skip through this pretty quickly, but so that was all in terms of U fluctuations. But if we look, we see this preferential strengthening of the small scale fluctuations in all the components, and we can certainly see this in Javier and Bob's DNS. So this top figure here shows streamwise velocity fluctuation in the log region. Black is going to be low speed and white is higher speed. And you can see these large scale features meandering through that domain. And if I just zoom in on some region here that contains one of these large scale features and draw a contour through the filtered velocity field, then I can define one of these large scale events. And what I want to do is compare that to what's going on with the small scales near the wall. So to show that, we're looking at the calculation of swirl between 0 and 40 wall units from the wall. And it's a little bit subtle, but it shows up in the statistics pretty well. But if you look carefully, I'm not sure how well you can see it, but there's a shadow through that swirl calculation. So the swirls are definitely weaker in the footprint of those large-scale structures. And we can also see that in the Reynolds stress. So these large scales are redistributing the small scales at the wall, and they're affecting the Reynolds stress as well. So for the final part of the talk, I just want to consider what this means at very, very high Reynolds numbers. We didn't have access to laboratory boundary layers up to 600,000, but what we were fortunate enough, courtesy of Joe, was to have access to this great facility in the Utah salt flats. I don't have too much time to go into details, but it's at certain times of the year, this site's characterized by very steady winds that come from predominantly from the north. And so we've got this nice fat boundary layer that's grown over 100 kilometers or so of smooth, featureless desert. And so basically, we decided to try this and scale up those hot wire rate measurements to reflect the length scales that we thought we'd see in the atmospheric surface layer. So we deployed a span-wise array of 10 sonic anemometers covering 27 meters in the span-wise direction. We complemented this with a wall-normal array of another 9 logarithmically space-censored, covering about the same distance vertically. If we're lucky, which we are often not, the flow's coming from this direction. And just to give some idea of scale here, that kind of dodgy figure lurking behind the measurement array is Min Chong. And to put all the scale separation stuff in context, 1,000 wall units in this flow corresponds to 10 centimeters. So that's about the third of the length of Min Chong's foot. And they're going to be living a couple of millimeters off the deck, down by the sole of his foot. So Min and that entire vertical tower is all in the log region of this boundary layer. It's all logarithmic. So so what we want to do is just keep our eye on Min Chong as we look at some of the data. So the color here is showing instantaneous streamwise velocity fluctuation. Red is high speed again, blue is low speed. So keep your eye on Min, and I hope this doesn't make anyone sick. Okay, so when we spin that around and we project those instantaneous fluctuations from the sonics in time, we can see that the atmospheric surface layer, just like the lower Reynolds number laboratory boundary layers, are characterized by these very large-scale features in the log region. The domain we're looking at there is 0.5 kilometer in the upstream direction. And when we put this in terms of presumed boundary layer thickness, everything looks like it scales pretty well with the laboratory measurements. And also to give some other details, the mean convection velocity here is about 6 meters per second, which means that entire domain that we're looking at there is going to take about a minute and a half to advect past Min Chong. Okay, so we can take that data and calculate other statistics, which we've done. So here we're looking at contours of cross correlation between the streamwise velocity in itself, so contours of RUU. And when we do this and normalize by boundary thickness, we see that everything collapses down pretty well onto what we see in the lower Reynolds number boundary layers. We see these elongated regions of positive correlation flanked on either side by regions of negative correlation shown by the dashed contours. This is a kind of telltale footprint of these very long elongated motions that Tim was showing in the log region. When we calculate the correlation of that streamwise component with the spanwise and the wall normal, we get some sense that these superstructure type events are accompanied by these roll modes or counter-rotating roll modes, which in the desert scale are actually kind of enormous. They're almost 30 meters in diameter. All right, so just to finish here, we'll go back around and look at Min Chong again and see what this means to him and these little viscous scales that are living down near his feet. So you can see that for elongated periods of time, then Min Chong and these near wall cycle are going to live within these enormous correlated regions that are presumably originating from the log region, these superstructure events. Not only that, but these large counter-rotating roll modes are going to mean that there's a span-wise converging velocity that they're also going to experience for very large time scales. And just as a final point, I just want to, I guess I just want to raise the question that if we're gonna believe in a wall-up mechanism for wall-bounded turbulence, then we've got to make ourselves comfortable with the view that something that's 10 centimeters long can grow into or give rise to structures on the 3 orders of magnitude bigger than themselves. So structures on the kilometer scale. And we'll just pan back to that photo. So, and hopefully everyone, you can get some impression of that range of scales that we're looking at in this boundary layer. Okay, so my conclusions are that superstructures are ubiquitous features of wall-bounded turbulence, and Jason Monti is going to show that they exist in other geometries as well. Their presence becomes increasingly noticeable as Reynolds number increases, not only as we get increasing scale separation, but also as the magnitude of those large-scale fluctuations becomes increasingly comparable to that near-wall cycle. These large-scale motions seem to actively steer the local production at the wall, so they're intensifying or weakening the near-wall cycle in their footprint, and that leads to increasingly inhomogeneous distributions of small scales near the wall as Reynolds number increases. And the final point here is more just blind hope, I guess, is that maybe these large-scale structures could have some implication to flow control strategies in the future. Okay.
Nick has finished in plenty of time for some probing questions. So, Bob?
With regard to the modulations and so forth that you might see in the solar, it seems clear that where that ought to come from, if you have huge scale separations, is that the local layer is seeing a smaller or larger shear. Right?
Yeah, yeah.
And that ought to come out as not only a strengthening and weakening, but also a change in scale. Is that something that you might possibly somehow be able to pick out of this?
Well, in the desert, we don't have the measurements near the wall. So all I know is,
but in the
yeah, maybe in the laboratory flow we could look at that. And I think that this modification of the shear in the footprint is, that's one possible mechanism for this. It seems logical. I mean, those small scales probably know very little about the superstructure. They just know that they're in a Reynolds boundary layer that seems like it's a slightly lower Reynolds number.
Exactly. And it's actually hard to imagine what else there could be.
The only other thing that worries me is these stirring motions from these roll modes. A span-wise converging flow is also a pretty weird flow to impose. It's fairly weak. I would say if you assume that, these are correlations, so it's hard for me to say, but I'd say if you assume that those large-scale motions have a fluctuation of something in the region of plus or minus 5u plus, then those roll modes, which are always conditionally averaged, they look like they have a strength at the wall of about, or not at the wall, in the log region where we've measured of about 1u plus. So it's fairly weak. But then it's coming out of a conditional view.
I'd actually expect them to be even weaker.
Yeah. I mean, I'm not even sure that they're there.
I think it
other
was
than in a
Hassan,
conditional
then
sense.
Rodham, and then back here.
Nick, to go back to what Tim said yesterday, it would be useful to take these various data sets in various facilities and see if the occurrence of some of these very, very long structures has a higher probability to exist at a given physical span-wise location.
At a given, you mean a given span-wise width or?
No, at a given span-wise location.
You mean they're spatially locked?
Exactly.
Oh, okay. So you mean some kind of problem with the facility?
Not necessarily a problem. I mean, but just so one would do some probability statistics and see.
Well, surely if that were the case, then I'd probably have some I'd have some span-wise variation in the mean across the domain. Is that what you mean? Or
not necessarily.
Okay.
No.
correlation.
Oh, okay.
Can you
Oh, yeah.
Rodham?
So you showed those long structures. Well, what was the longest that you observed?
In the desert, then I mean, this comes back to what Tim said. There's a distribution of scales, I think, and the problem is with the desert is that we've got 1 hour of good data, which is only 360 boundary layer turnover times. In the laboratory, I've got tens of thousands of that. So, I mean, I would say that the longest structures I see in the desert, I don't see anything that's huge. I mean, the longest I see is about 6 delta.
What?
About 6 delta, so about close to 400 or 500.
One more quick question and we will have to move on.
Just wanted to be sure that you're not seeing residual effects from earlier in the day. I mean, the convective structures could be much larger.
Yeah,
They have a longer lifetime,
Yeah.
so an hour may not be enough time for them to have disappeared.
yeah. I mean, it's hard to well, maybe Joe knows something about this, but in the atmospheric surface though, then you're always a bit worried about what's happening upstream. And you're right. You're actually looking. You're looking at things that happened hours ago. So, and yeah, you're looking at things from periods that weren't neutral.